Billard's lab in EPFL, and Miao is going to speak to us about driven and haptic guided fine manipulation of objects.
Thank you. Hello everyone. Today I would like to present our recent work on vision and haptic guided fine manipulation of object merely and from NASA EPFL, Switzerland. So to start with, I will first give a quick outline of the talk. We know that your human hands have 4 different kinds of capabilities to sense, to explore, or to grasp and manipulate, and the last one is to make some gesture. So in this talk, I will only focus on the middle two parts. The first part is about robust grasping and to manipulate the object dexterity. And the second one, I'll talk about some initial result about the bimanual object tactile exploration. Okay. So in the first part, our goal actually is trying to transfer human grasping and manipulation knowledge to a robotic hand. And we are looking at this problem in the framework of impedance control. So our goal actually is to try to specify the desired object level impedance control for robust grasping and dexterous manipulation. So usually people look at this problem either by transfer this hand grasp configuration or just transfer the grasping point to exactly to the robot. But here what we are trying to argue is that actually we can look at this problem from the point of view of the object, and we transfer exactly the same dynamic behavior to the robot hand. So why we look at this problem in the object frame? So usually for a stable, for robust grasping, the goal is to try to keep the object stable within the hand. And for dexterous manipulation, our goal usually is to try to move the object from one initial configuration to desired goal configuration. And both of these tasks, actually, we are mainly care about the object. We want the object to follow our expectation. So it makes sense that we look at this problem in the framework of the object, and we don't really care about what hand we use and what kind of the embodiment of the robot we use. So in order to specify this behavior in the object frame, let's first look at the object dynamics. So here is a simplified example of object dynamics. This is an object and it has 2 forces applied on it. One is the force that we can control, is F. Another one is the force between the object and the environment, F in V. So with these 2 forces, and we have the object has an acceleration, and we specify this desired impedance behavior as a typical impedance controller. So here M, D, K are the corresponding to the desired impedance initial, and D is the desired damping, and K is the desired stiffness. And XD dot and XD is the desired desired velocity and the desired position. So with these 2 equations, and we can come up with the closed loop dynamics of the object. And we notice that if we set the desired initial identical to the actual initial, and the last term can be cancelled. So we only have these first 2 terms. So here, this x and x dot is the actual trajectory that usually in a task we need to measure it either from vision or from the forward kinematics. XD is the desired trajectory. We need to plan this beforehand and use some motion planning technique, or we learn this from human demonstration. And another important part is the parameter for this dynamics is the damping and the stiffness. So in our work, the actual trajectory, we measure it using the concept of fertile frame. Basically, fertile frame is just a function of the positions of all the contacting points on the object. We are exactly looking at the dexterous manipulation. This is a very challenging task if we want to make a plan beforehand, because the uncertainty of this problem is usually will cause a failure. So we look at this problem by using human demonstration. So human demonstrate this task since our learning is conducted in the object frame. So just kind of simplify this problem. We record the object motion, and we also record the contact force between the fingertips and the object. And we formulate this problem as a constraint optimization problem. So this constraint comes from our assumption that we assume that first, the stiffness should bounded. It should not be an infinitely large stiffness. And second, the actual trajectory should not be too far away from the desired trajectory. That's these two constraints come from. And by solving this optimization problem, we can obtain this desired trajectory that shows as the red line here, and this blue line is the straight line because we scaled it. So we can see that the actual trajectory, the desired trajectory indeed is not too far away from this actual trajectory. A more interesting result is about the rotational stiffness. So we can see that in the first 80% of the task, the stiffness is almost constant and it's very small. That's because in the first part of this task, when we try to insert a bulb into a socket, the resistant friction is always very small. And in the final 20% of the task, we can notice that the rotational stiffness increased significantly. That's because only in the last round of this task, the friction suddenly increased. There's like a hard nonlinearity in this problem. So we try this experiment like 10 times. We can always obtain a very similar profile of this stiffness. Since our learning is conducted in, as I mentioned before, the learning is conducted in the object frame, so we can easily implement this in a robot hand. Here we use the Agile hand. It has 4 fingers, but we only use 3 fingers. And each fingertip is mounted with the Biotech syntax. It can provide contact force and contact position. In our experiment, we only use the contact position. We don't use any feedback from the contact force. And there's no mission to track the object. And the motion of the object comes from the virtual frame. And we repeat this experiment like 10 times. We can always obtain a very high rate of success. It's around like 8 times of success out of the 10. Another part of this talk will about bimanual tactile exploration. So this is also a very interesting capability of human hand. And for example, we grab a purse from our pocket, and we use one hand to grab it, and another hand we try to find the correct card or find some cash to use it. And this is also why do we need to use 2 hands? Because I mentioned also kind of mentioned in the previous talk. If you just use one hand to explore the object should be fixed on the table. Otherwise, when you explore it, the object will move. So another important reason is that we need this 2 hands to kind of extend the workspace of this exploration. So when we explore one side of the object, and then we want to explore the other side, and then maybe we just rotate it. Here is the setup we use. It's ICAP platform, and this weird structure here is the vision to compensate the forward kinematics. And we use text scan mounted on the finger to provide the contact position. And we have in the following slide, we will talk about the filter we use to filter the data, and also how to select the task in this task. So why do we need the filter? Because this tactile data we obtain is usually non-uniform distributed, and it's very noisy. And when we identify the object, it will be very time consuming. So we use the GP to filter this data. Basically, I will just skip this detail of the mathematics here. The key idea is that when a new data point comes from, we will use the GP to predict the uncertainty of this new data point. If it's very uncertain, that means this new data point may be very important for our model. So we just keep this point. And another criteria we keep the point is that this GP, because it's augmented with the derivative information of and then it can predict the lower direction of the next point. When the predict lower direction is not coincide with the measured lower direction, or that means this path, the curvature, change rapidly. So that means this area maybe have some interesting feature. We want to keep this point, so we also keep this point. And here are 2 examples. The first example is just some point cloud that we get from the internet. It's Bunny Rabbit. We can see that it has more than 50,000 data points. After the filtering, we only have like 71 data point. The second one is the data point we get from the real bimanual exploration. And after the filtering, we can see that this data point we only have like 51 data point, and we see this data point becomes more like a uniform distributed. And we identify this object. To create the object model, we also use human teaching, and we just press the fingertip and we get a point cloud of this of each object, and we use it as a model. And during the online exploration, we try to identify or to match this data point we get online to this model we obtain. And for the grasp selection part, so after the object is identified, we are trying to select a grasp for this given object. So we kind of teach the robot which part of the object can be grasped. And we also use a human demonstration here, but this time we model this graspable area using a Gaussian mixture model. It's a properties model that can give us some information which part of this object can be grasped, and it's model this area as a likelihood function. And during the online grasp selection part, we just select one of the most fit grasp from this area. So we define the objective function, and this objective function tells us how far away that we are from this graspable area. And we select this most close grasp, and we show some picture of the result for this fiber grasp. And here is it's just a video that we show the whole procedure for our bimanual tactile exploration. And I think I will just stop here. And if you have any question while watching the video, I would like to answer.
Is there any questions for Miao? Dazzled everyone with his presentation.
When you speak about representing everything in the object frame of reference,
Yeah.
you mean that you have like a Cartesian frame of reference on the object, and
So
then
you only carry about the dynamics of the object. So you define your learning framework in the object frame.
yeah. So you mean that you have a Cartesian frame of
Yes.
reference inside the object, and
Yes.
then everything you do. So don't you have then a problem of calibration when you want to do the action on the object, like?
Because we use the 30 frame. So this 30 frame is designed immediately when all of the three fingers contact with the object. When it's contact, and then the object frame is designed at the center of these three contact points, and it's unique. So there's no calibration involved in this task.
Any more questions?
So just that point about the 3D frame, that means that you have an assumption that the object is rigid, like it's not like a
It's not-
floppy toy or...
Yeah, that's one of the assumptions, that it's rigid, and also it's assumed that there's no slippage between the fingertip and the object. So when there is a slippage between the fingertip and the object, then the virtual frame and the actual frame of the object will have some mismatch.
Right.
This is the main reason that caused the failure of this task, of this method, and we are trying to compensate use vision. That's why I put the title that vision, but until now we didn't finish that work.
Okay.
Is the paper in the e-card proceedings?
Yes.
Okay. Thank you, Miao.